Let's beat this up as many ways as we can, but it's mass hysteria, forgetting that you had knowledge of something that doesn't make sense. It's sort of like you're getting 10 great compliments and one negative. One negative can control everything. Well, we have the OSHA report showing that, or implying that 11 sheared 12 off the deck. The problem we have is we have a video that doesn't substantiate that. We have a video showing a break here and approximately a break here, one in the deck here past the node of 910, and here. This is where we have a break. We do not see the base of 12 being slid off the deck in shear. To get them to do it, he has to do some extrapolation showing the shear sliding moment, discounting the steel that's inside the structure, discounting it, taking it away. Also discounting the cracks that are present in the structure for this to happen. He discounts any shear inside here because he says undeveloped. Take note of this very important little shelf here, this lip. I'm going to show you something, and I don't have the back of this to show you this other part of concrete. But I'm going to zoom out and I'm going to show you. I'm going to show you. No, we've already been down those roads, so we'll keep those roads as they are. That's the previous videos. You guys can please go back there. But he discounts the engineers that do that report, part of that report. They discount that this member number 11, after detensioning, before the sliding event that it is claimed to have taken place, or perhaps it's taking place at the point of detensioning that he's claiming that a sliding event is taking place against number 12 at this point. Well, a sliding event would have to be pressure against this. It would have to be a load. Oh, that's going to be some good data to share there. That's another video. I don't know if I'll load it yet, but it has to take a load. It has to be taking a load to have this sliding event, this pressure. Do they calculate how much it takes to push number 12 over? They do not give that to us. They give us all types of lack of clamp force, and this release of the clamp force now allows number 11 to slide and push over. But they don't tell us how much it's sliding and pushing over. How much of the dead load of 12 is it able to slide over? The dead load is also including the canopy's dead load on top of number 12 pushing down. They don't do the deductions for that as a counterweight, as part of the abutment, if you will, that it has to push. Also, they don't account for the sliding. For this to slide, to move over, this deck has to creep down. If the deck creeps down, this puts this in tension. He just has it magically when the force is released, which you already had, let's call it 600,000 pounds of force already applied to this, that when you release 600,000 pounds of force, that this then becomes in compression different than the force you had. So this force I'm talking about would look like this. So he's saying this clamping force is why this happens. You can clamp it, and so it can't slide while it's clamped. Okay, I like that thinking. We release the clamping force. Upon releasing the clamping force, it now slides, pushing 12. And he discounts any reinforcement that's in 12 as not developed. So it's no resistance counted for that. Apparently, he discounts that this was not rough, and so he discounts that as being an ability to counter the slide friction that he's talking about, or they're talking about in the report. But they don't show that if this to slide, this has to move. The base of 11 has to move over. If the base of 11 has to move over, we have to have a failure in the canopy, or we have to have all the base of 11, all of the truss members here move over laterally. And they would be moving over from what? From the dead load of the deck, causing a downward force pressure that would make it slide over? Or would the deck not be part of this anymore, and the downward force of the deck's deflection cause an outward pushing of number 11? The elongation is the issue, and he addressed elongation with the, as I stated in other videos, how somehow the forces aren't carrying over to D1 and D2 and D3, all the way down to D6, transferring the forces. So he made it in a zonal, as I talked about. It's sort of like a zone. I made that out here. Not necessarily in here, because this is also and because I have access to the cracks. Access to the cracks show me they're in tension, not in compression. That this member is in compression in a rainy day, maybe once it's under tension. But when it's detensioned, these cracks are open. This is not sliding. And if it is sliding, how do you account for it's only this much allowed to push? Remember, this is sliding across the deck. He did not do any deductions for the part of the deck that's sticking through this. If you recall in previous videos, where this has a and B post tension bar. A and B are A is inside the deck, and B is inside number 12's tag on, which I call a blister now, sticking outside of the diaphragm, a bump out. That's what number 12 is also supported by, and a clamping force. Releasing that clamping force, I think, allowed the part of 12 to rock downwards, and at some point the bar kicked in again because it wasn't totally detensioned. It was detensioned, but the nut wasn't totally taken off, and it was able to grab again. I'll show you some images in a second, but I need to go to the top of this. I really want to show you the beautiful, what we're looking at here. I do not believe these were pushed over too far forward, because of the, I don't believe they were pushed over too far forward for me not to explain some of these bends in this bar. The bends in this bar, I think this bar was originally straight as in design, and this is showing before it was broken free of number 12, the deflection that took place in number 12. That this bar is clearly not the shape of this bar, so this shows you a torque action took place during the failure. I wanted to get to more of that later in another video, and we'll even talk about these bars here, and this bar here, and this would help us with that shear path if it was taking place. This is showing the initial, I think, probably downward deflection at that point. There is a bar inside here, a rod, but in the images they show, and a piece of concrete was back here, behind here higher. So these images are not all telling. Things have taken place to change my ability to evaluate. For example, this concrete is not correct, and I'll show you in a moment. And this is not correct. The bars are no longer back in place here at the new staging area. This is number A, and it states sheared, implying that the lateral movement across the deck created a shearing, but this is implying it. This is not true. And if it was sheared across here, why is this not plowed in front, as far as the shearing of all the forces of the structure? Well, because the concrete was breaking apart, that this actually did participate, and when it participated, it cracked the bottom of 11. And also, when the front part was in place, this acting as one, we see the tensile breaks in the top of 12, also top of 11 also. This is the deck. It's only about 9 inches or so, I'm estimating, of left of number 11 at this point, sticking off the deck. So the sliding would be pushing this off the deck. But we only have proof of a limited amount of sliding, and we have no proof of 11, the bottom of 11 being A, participating in this sliding, because we see it permanently locked in place with concrete in front of it. So it didn't have a sliding pushing event forward. It would have just been the concrete only at this point with this material. Now, the top of it could have had a buckling component to it, the top of 11. But I don't see it having with that little bit of concrete left, I don't see it having the ability to push over anything. Again, there's no bar post the bars that this bridge was supposed to be clamped down. They're not present in these images any longer, and the pipe is now presented as cracked, and no bar inside of it. Why did they do that? Why didn't they put it back for the best evaluation? Put it back to where you saw it at the bottom of the bridge. You know, this moving of this structure, moving of this was uncalled for. It was uncalled for. This should have been like an archaeological dig and evaluated. In fact, maybe they should have just used archaeologists, since these engineers and OSHA people, and along with NTSB, don't know how to properly dissect a structure that has a chance. I think because they're so in dire need to get the bridge back open, the road back open, is more important than getting to the proper data. So they're going to have to do some guessing, extrapolation, and jam it down the public's throat. Here's what I mean about that bar in place, and there's that concrete again wrong. But we look at the right. We look at the OSHA, the NTSB's video, and we see here is what's really presented. And what's important is the bar has bent to some degree, and this would tell us to what degree, and concrete's inside of it. This stuff told a story. It's told the story that we will no longer be able to tell just by looking at this alone. That I've got to do some extrapolation, running back and forth from images, etc. Here's the bar apparently on the same angle. The debris field, if you will, is very important. This shows all the shattering that took place, the dramatic shattering that took place, and the amount of force that would have done this. Now, I'm not going to count number 11A as part of that dramatic force. We see it embedded. So the force that I'm counting is this dramatic force that made this debris field. I'm getting from the 280,000 plus kips of bar number B. These are the shims. They appear not to have been anchored down. They're here now. But look where they are. They're on top of the bridge at this point. So they did not come down along with the bridge. So we see that some type of, hopping took place. And then a flipping action of this, while it's on the bridge, is hopping off, flipped it in the air, and came down to this point. This was also data. I would be able to determine that flipping action, etc., just by looking at which side's up and which side's down. But it wouldn't give me too much. But I would take the data anyway. I'd also want to see the imprint, if any, that's left behind on this. It's a thumbprint, if you will. So we can see how flat it was. And that would have been on top of all those members. This is a very telling piece of material. I would love to know where it goes. Then what we have right in front of us are some rods that appear to have broken free here and here and are straight. Where did these rods come from? I can't see the rest of them, but it's very telling data, and we're missing it. These are both bent at different degrees. This appears to have taken 2 bends. This appears to be sort of taken on the path of the 2 bends, maybe 1 and 2, but not as sharp, right? Not as sharp. So this is the torquing action going on. Or torquing action, this one holding on the longest, apparently. But this is that back and forth. It could have broken and failed at that point. It got to that degree. And then this one didn't fail until it got to this degree where it came out. Looking at the underside, okay, looking at this nut again, we can count these threads. If you knew the pitch of this, say it was 13 threads per inch, and you could figure out that they detension and they moved it 3 threads, you could extrapolate that three rotations they loosened it up by. They might have reported when they detensioned, and you can determine it's 3/10 of an inch, 3/13 of an inch. That this bar dropped down, equating to the cracks we see at the base of 12. We're going to get the base of 12 real quickly, I think, if I can find the image. So I did another video, and it's 30 minutes long. Perhaps I should present that first. I don't know what I'll do by the time I'm presenting to you guys, how this will look. So I'm talking to you, just giving you thoughts. I don't know if I'm presenting this one first or the other one now. I need to get more images to show you. I want to show you again tension. 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 Right above this pipe is where right above here, right about here somewhere, is where, not up to this point, is where and right about coming out to the end, is where number B, the path of B, post-tension bar B, is located. This is after detensioning. This is on March 14th. There's no tension applied at this point. They detensioned. If the structure was being pushed off, you wouldn't get right, this crack right here it would be compressive. It's being pushed off. You would not see it in a well, it's being pushed off. You would possibly see on this end a compressive moment and an open cracks here. So it'd be tighter here and opened here. But if this deck was dropping down and say at number 10 and 9, and the 11 still having to participate, those two together interacting would create a hinge effect that could open it up to this capacity. I still like to see a little bit of compressive cracks back here. This is very important. This different coloration is going to help us just beautifully so. Beautifully so. And I'm going to show you that in a moment. It's going to define, this is defining the base of, right about here is defining this line, the number 1 bar, post-tension bar is in the deck right about there, and this is where number 12 takes over. Number 12 is about 3 1/4 inches below the surface, so right about here all the way down. Approximately right where this crack is appearing right here. This apparently is the path of this path right here. This crack line is the path of post-tension bar B. It's A and B, and A is down inside. I'm making sure. I just want to get this right. Visualize this. Yeah, this is the top section. So this is A, and B's down here, going a different path. I'm sorry, A. This is B going this way. And that's your path. This is what the report is claiming, that all this section here pushed this direction. We already have a crack now. This is a failure of the concrete around it. This is not going to be a crack. I bet my last dollar on, not my last dollar, I bet dollars on that, legal dollars on this, a legal bet, that if this was experiencing a sliding moment, that you would see a separation here, not in this capacity we're looking here. This is a tension release break. It could be a compressive break when they're tightening, but we know the date to be on 310 after the detensioning. So this, we extrapolate, it's a detensioning break after detensioning. This means already the deck is experiencing creep. This is when I think that at this time, this is when the releasing of the forces regrabbed on the back of the top of in the canopy where they loosen the nut up. If they were to try to undo that nut, they would have probably found it was taut, that they would not be able to do it by hand. This on this side is claimed to be 314. Many days later, don't not get this confused with 310. 314. It's starting to look like this. It does look like this, apparently. This, I believe, is the torque action from the back of there. The elongation in number A took place. And we actually have the measurement down this hole. And it's saying that the gap here is 3/4 of an inch approximately to 1 inch. So that's our elevation. If we take away maybe 1 inch, if we start 1 inch here, we can then come to this crack here. It's coming across at 8 inches. I can then figure out that this crack is about 7 inches off the bottom. 7 inches off the bottom of this deck. I can use that, what they thought they were directing me to there, and determine the rest of the cracks and try to scale this and rotation, etc. Here's where this is 12. 12 is separating, and the concrete was poured all in one pour, 12 and 11. And we can see 12 and 11 at this section is apparently having full contact of concrete. Not so. Follow the 12 down again, 12B, and you can see this pattern is continued down. That I believe the falling away of a hinge effect of 12 can identify these cracks. If only he did not put this thumbnail picture here, perhaps inside this section I would have seen a compressive moment here in the concrete to help me verify that. I am not going to be able to see that. I want to see some spalling here. I want to see some spalling. If I can't see spalling, I'm going to have to somehow allow this thing to release away to some degree. And his picture that he puts there blocks that. We can get a pattern of this crack, and you can put it back in place. You've got 8 inches, which is really approximately 7 inches off the deck on this side. Or on this side, it's approximately 7¼ inch. On this side, it's approximately 7 inches. However, you'd like to try to reevaluate this. These not being a break right down here, I can actually say this is elevating here at this point. And this side of the on the deck area is not elevating, or we see a hinge at this point, is what I'm driving at. This shows a hinge. And here's our effect of that hinge. So we see this is now apparently higher than this, just by a slight bit. Remember, it's exponential as we go. These lines right here are interesting. They were created when? They were created beforehand, and now these are days later, and now we can see the separation of these lines. Here, not so much. Here, yes. And these are coming in contact, so it's a flexural line, if you will. These, not so much. I mean, they are separated. So if we can figure out when these lines were created or when it was photographed previously, those lines will tell a story too. A percentage of movements to scale. We don't have access to that line. We do have this line. It will tell a story when this is photographed previously and what's taken place. That's the opposite side of that torque action on the other of what we were looking at. I think it's down here. Let's see. So this crack, this little stair step scissors tooth thing appears to be right about here, and there's that crack going down horizontally. We can't see it. It's up here then. All right, so loop up here, line, table. Let me do this. Crack down. Loop scratches. All right, so right there is the joint. Right about here is the joint. I follow this line down here, and I get it crossing there. There's that line, so out of view, it crosses there. So beyond that, where's that line? So we've got approximately, visual there. Just trying to visually put it together. So right about there is the retake of it. So if we shift this over about 3 inches, it appears that right about is a little bit of skip there, but there's the line, and here's a continuation of that crack. This report does no deduction for this. No deduction. It doesn't account for it. It doesn't account for this crack at all, whether it's compressive or tension crack. It doesn't account for its lateral movement side to side. Take note of that lateral movement side to side, which I think the report is trying to allude that this lateral movement is trying to imply that at the base it's a sliding movement. And I'm going to show you that with just implied images, if you will. Right here is the top of it. That's a lateral movement. See the lateral movement? Lateral, not a sliding. These match at this corner here. This slides over. This is a torque going on. This is a slide. This belonged here. This is that direction. I think the numbers show that in the previous videos I talk about this stuff. And I apologize, I do long videos, and so now I realize that to get this stuff out here, I got to do smaller videos. So I think I'm going to terminate right after I give you this food for thought. And yeah, I'm just leaving you food for thought, and then I've got to add to it and add to it. We're ultimately looking at probably, oh, really? My startup disk is almost full. It's going to hurt me. I'm not sure if I'm going to be able to record this without figuring out how to delete data. Oh, no, wrong hard drive. Let me pause the video and let me come back. Let me fix this. Let me pause. So let's talk about what we're looking at here. This is the north end. As it's described in the report, this is pushing away. number 11 is pushing away. But perhaps 12 is pulling on 11, which then creates our tension. Meaning 12 is the weight of the end of the structure, the diaphragm here is as I said, not developed enough to hold this blister and the loads coming down 12 in such a cantilever effect. And I say cantilever because there's no shimming underneath of 12. Also, it does stick off the deck to some percentage, some percentage of the columns width, and that load transfer at the outside, it puts the column in not in equilibrium. The column alone now, not in equilibrium. And that's all it needs, the forces on the outside. In other words, you don't need to see this column 50% on the deck, 50% off the deck for this to establish this deck area. That perhaps you only need, the loads could be more so on the outside of this per the design, the canopy design compared to the deck design compared to the column design, which is actually at a plumb by what, 2.5 or 2.5, 2 3/4 inch, something like that. But I also state that this has got almost you're pulling at the top to create this elevation here. I have to create this elevation, and I can't just get that by pushing the top over or allowing the bottom just to drop. You just can't get it dropping and have this coming up unless you ran into a conflict of metals inside the concrete, which would then cause us to spall upwards. So we would need to find that metal, that conflict, to support that part. So let's see if we can find that, and let's go from there. So now I find the metals that I just spoke of. I find rebar sticking outside the deck. So if this was to be dropping down, as I initially said, and having a slight rotation, this would get your counter force, your spalling coming upwards with this guy. Watch this though, as we look at this member here again. As we look at this member, we pull in. Number 12 slid over, and we have a tape measure to show a torquing action going on here also. It slid laterally, and I'm saying 12 slid and not the deck. So so we have it, but that is on. So the date of that is on the 14th. This is before the next day. It's going to collapse. The structure is going to collapse after trying to put it back with post tensioning. So the same thing here. I get an elevation. Now, can I say the metals did that? Well, we see the metals in here and the photograph. So we're coming back to that 314. Can I still get the same effect with the metals back here? I don't see the metals doing it back here at this time, having that same upward spalling effect. I think this is that torque action, as I show here, the sliding. Oddly though, the sliding is out here, sliding opposite direction, that direction, and so sliding towards us. And the reaction is as we see it. So here's the slide of this. This number 12, I'm sorry, I keep thinking 12, the clamping force. The rod's inside there still. It's not clamped at this point, but it's still in there, and that could have stopped it from shifting over more, whereas the bottom is in the deck. So this is your deck, the A, post-tension bars A is in the deck. So you get two different reactions here. One's being held by or going along with the outside, that's B, outside rod, and the rod down here is not going along, it's inside the deck. So you're getting that counter torque, well, a slide to side shear reaction with the two different members playing differently. And let's get the two different members playing differently. These guys, this is in the deck, that's that lower part. That's A, I'm calling A, and this is B. That when this 12 column right here slid away, as we see in the images, that it had this torque effect and it presented itself as those cracks. And it slid away because of the detensioning, and this thing just, trying to fall off. It's rocking, it's kind of all the forces coming down here trying to set itself and stop itself only by the rod back here. Then when they detensioned it, it was loose, as I stated, and I just would probably collapse right then as they'd taken it fully off. It stopped, jerked, And that jerking effect over the next few days, along with creep, has effect we see of what we're looking at, these rotational shapes, etc., these torques, these cracks like that. This one at the bottom, I think I've already explained that. This is right about here is number, the rod 1, rod A, post-tension rod A, right here coming through the deck. And as that did that drop off moving around, that this part of this last chamfer, 8-inch chamfer, if you will, just indicates what's going on, how much movement took place between here and here. Using those measurements alone, you can determine how much this deck had to fall if you had true measurements and you had the time to do the extrapolation. And I mean the full gap, not the spalled out area. It would have to be a gap you would really determine. This is still spalled, so that would be compressive pushing, so that wouldn't work for me for getting that one. This is where sliding is supposed to have taken place. This is 313. This is 2 days before the failure, and they're claiming sliding. I'm saying this is tension. You see the break? It was sliding. We'd see some cross shear action going on here, and more breakage than this. Cross shear action. We'd also see the little shear action into here. This is a bar here, and as this is trying to slide over, it would want to crush this up against that bar. But on the other hand, if the deck was falling down over here by the node 9 and 10, falling down, this would create this separation that we're looking at, the creeping down. This piece apparently comes out of there. That's that torque action I speak of. It's got a date stamp on it. This is that torque action again, and this could be simply as the stirrups inside there. This I find interesting a couple of times over. I don't know exactly where this is, but it appears to be part of this photograph here, doubled up, and then following down. There it is. It's multiple information about it, but this should just be number maybe bar 1A. Coming across there that they just zoomed in. Here's a little crack there. But this is that sliding action that they're alluding to us in this photograph, that took place. As we zoom in, we see it's breaking there. We see it's breaking, and this should be number 1. But that sliding action is a lateral side-to-side action, as I just showed, and we'll show one more time. That this is a side-to-side action and not a off-the-deck action here. This is, I think, I still need to evaluate the concrete inside here and how it had a shimming effect on this. Is on 313. Again, now I think this is being restrained by the post-tension rod A at this point, B, the top rod. Otherwise, this would have already collapsed. My theory. So right here, this tape measure shows our torque action again. That's about 5 inches on that side, and we're not supported here. And the only support holding this on at this point, I think, is the clamp action in number B, which is coming through here and above the pipe, which is right below this. The pipe is, so it's right above, parallel roughly with this, parallel. And right here is the other side. But again, the tape measure, you do have to do deductions. It's not properly underneath D1 like the other side. It's on an angle, so you'd have to straighten it up. And maybe you're at around, I don't know. So this appears to be lower over here. Maybe, I don't know. You're somewhere between 3 and the other inches on the other side. This would also have to be taken consideration that this deck, this pure top is level, and that it's equal in distance from here to here before the cracks on each side. These cracks are tension cracks, I think, and at this point, I can only get tension cracks by the deck. I have to involve the number 12 doing a torque action using the tape measure, and even a leaning in action towards number 2, if you will, doing extreme, which means the bridge took a rack, because I can't find compressive in here. This is clearly together. It didn't break separately, and we have cracks in this pattern. This is inside the clamp force area of that number B rod. And this is most important, beautifully so, because now I have images to prove to something else for you guys about what's going on. And I'll go to that just about now. Just about now. So awesomely so, I talked about, no, you know what, I'll make another video of that part. I'll make another video of that. Where are my images? This other image is another image I'm looking at. Let's wrap it up with this one and part of this to keep reinforcing. So number 11 is claimed to have pushed 12 off, or started the forces to push 12 off, but the cracks don't show that. And here we are again. You're going to see the base of 11 pretty much hold strong until the last moment. That's because the canopy and the bottom of 12 is still engrossed by B, not A. A is in the deck. It's not help. What you're watching here is we're watching a reaction of B, not the one they last tensioned, which is A, but the one they tensioned before. We're watching how it's holding on. So the bridge is falling. The base of 12 did not push out. If this was pushing down and 12 and 11 was able to push across, this is the time it would be doing it. This is the creep, the most creep you can have. And this would be, I'm calling it creep, right? This means that 11 would be pushing out at this point, would be pushing out the greatest at this point. There's a creep, and if this is acting as a truss system, which many of you engineers keep trying to get me to see it as, and that's because you're not accepting that you're not looking at a truss system. And you're not accepting their interactions of how this stuff is really, what you're really looking at. Except that if it's a truss system and this is going down, that this will be pushing out. But the rod, number B, is actually working still at this point. So much so that it won't allow the base of 12 to kick out until it gets beyond, it's really just, it's going to fail ultimately. But we're looking at the top of 12 going the opposite direction. So base of 12 is still outstandingly supported, if you will. There is no pushing of 12 out. If any time, again, it would be this. The blasting out now would have taken place of that blister of the back of 12 taking place, and possibly the dramatic crumble, all the debris we see in the images here is what we're looking at now. The reversal is going to take place in just a moment as this comes around the other direction. Now here's our flexing happening here, flexural happening, but there's some type of connection here that's pretty damn awesome because we know it's going to stand proud still. There's 11, the base of 11 now going along with the nodal area here. So it doesn't have the ability to elongate. It's going along with it, so it has a pulling effect in the deck. And we know that number 11 is going to, number 11, the base of 11, which is A, is going to ultimately rip out the bottom of A. But as you look at this, you have to extrapolate that if the B post-tension rod is still connected to the base of 12, this is where, if you can visualize, this is the rod. It's just 12. This is 12B coming down. At this point, it broke through the top of 11 fully down here at the nodal area, the top part of it, at the top part of the chamfer, not the deck chamfer, the top part. And now it's inside 12, and it's going to cause some, it's going to rip through at some point. It's going to keep ripping up here just a little bit, and then it no longer fails in here anymore. At that point, we can extrapolate that it's now also any resistive forces left inside here can no longer have the resistive forces to start shearing and pulling out the rest of the links in the top of the number 11, as we see it stand against the images I need. As we see it stand, and I guess I should pause the video. I think I can get to it real fast at the bottom, though. I think they're at the bottom, right? So as we in the report, as we see it in other places, obviously, as we see it stand against the pier, well, I guess it wasn't quite at the bottom. Right about here, though, I think he just uses. Oh, great! I really apologize for this. You guys' time is valuable. His time is valuable. As we see leaning against. Here, that this rod at this point is no longer can keep ripping, even though it's in the air, but then the bottom rips out. And so this is what we're looking at this point. As I think the rod is here, and it now creates the debris, part of the debris field. It's de-stressing itself, if you will. It's no longer participating. It will pull and lay on top. And then it's going to be a secondary bump here, and where the deck is in the air, this is already on the ground. What's pulling this deck down and pulling it away from the pier and falling down? It could be the elastic ability of all the post-tension rods in there, or it could be just the momentum of it going forward and flipping it. But I had one more way of pulling this down, and I forget what it was, believe it or not. Yeah, I forgot what it was, but I had another way for that to happen. I just wanted to give you guys a quick more data, and I'm going to give you a teaser and talk to you about how I'm going to explain where all this developed with the images I was able to locate rather. Thanks for watching.